Okay, let's get started. So this is lecture 3. On the interplay between polymorphisms and CSPs and more. So just to quickly recap what we did last Friday. So we saw this Galois connection, or we saw it 2 weeks back, but then we established it last week. Namely, if you have two things, so if you have polymorphism of A is subset of polymorphism of B for two constraint languages A and B, that implies CSPB reduces to, in fact, let's say polynomial time to CSP. Okay, so in fact, it was a very local form of reduction called the where you just use some auxiliary variables, basically a local gadget reduction. Okay, and all right. So, and then using this, and we also saw this thing that basically, if you have rich polymorphisms, implies algorithms, and life is tough under dictators. So if you only have dictators, only implies hardness. Okay, so and this part is pretty easy, at least if you just assume that the only operations which preserve the relation are dictator functions or projection functions, then pretty much it follows from this Galois correspondence that you can reduce, because then your polymorphisms is sort of minimal. So then you can take B to be some NP complete problem, which everybody will have dictators, so you can take B to be say 1 in 3 SAT, and then that will reduce to you and then you will be hard. Okay. So that part is easy. That's for the Boolean case. For the non-Boolean case, it's almost like this, but it's a little bit more technically. You have to be slightly careful to get the correct thing, which we didn't fully discuss. I mean, it was basically whether you have these W and U or not. And the most of the action really happens here. So when you have rich polymorphisms, you get algorithms. And obviously, life is easy if you have very rich polymorphisms. So last time we saw 2 examples. So we saw if you have totally symmetric or symmetric polymorphism of large enough arity. If you have symmetric or totally symmetric polymorphisms of all large enough arity, of all large enough arity implies algorithms. In fact, the totally symmetric case, it was a very simple width 1 algorithm. In this symmetric case, we wrote the LP, and we said the LP was, if the linear program, which is a very natural linear program, said you're feasible, then indeed you're feasible. Okay, so we proved these 2 things, and these are just like some teasers of just the most simple form where polymorphisms govern algorithms. So what I want to do today is that I'll come back probably to something where we will later on see that if you have majority of all odd arities. So we already saw this, any 2 CNF or Boolean thing, the majority on 3 things is a polymorphism. And because you can do this composition and projections and so on, you can get majority of all odd arities. So whenever you have that, that implies algorithm. And once again, in fact, some LP works. Okay, with some slight caveat. So I'll try to get, this might be the technical thing I do. I'll come back to this, sometime today, I think. But what I wanted to start with today is to give a glimpse of things beyond CSPs, because so all this stuff which I talked about was very classical stuff on CSPs. So I want to talk about beyond CSPs or beyond exact satisfiability of CSPs. So far we have said, I give you an instance of the CSP, you have to tell me if it is satisfiable or not. But now we can talk about few other variants of CSPs. So it's not still completely something unrelated to CSPs, but just problems which are more general than this. So the first thing we can talk about is optimization. Okay, so this is usually talked about as min CSP. So what do I mean by this is that I give you a collection of constraints, and it may not be satisfiable, but you must find me an assignment which minimizes the number of unsatisfied constraints. Okay, so this is min CSP, minimize number of unsatisfied constraints. And this is a harder problem because if you had a subroutine to do this, you can just do this. If your answer is 0, you know it's satisfiable, otherwise not. Okay? And more generally, you might have weights on relations and stuff. So instead of just these predicates, you might have general functions. So in these predicates pi in gamma, which we talked about, I won't be too precise here, but this will be enough to give you a flavor, will be replaced by some functions which are from this to say finite values. Okay? And the goal would be that whenever you apply pi to some set of variables, you will basically apply it to that particular assignment and you will try to minimize this. Okay, so the goal will be something like minimize summation over all constraints of pij of those variables. What is this? J1 xj arity of ij. Okay. So earlier you just wanted something which satisfies, you put a giant and here, but now you will just minimize this function. I mean, you can also think of maximization, but somehow traditionally in the field they think of minimization. Okay, because one canonical problem which is easy in this case is like min st cut. So I think traditionally they have talked about min CSP. So again, now the question can be, suppose they give you a collection of these functions, some finite collection of functions, and I want you to address the complexity of this problem. Okay. So again, so it turns out here also polymorphisms play a precise role. So tractable, so a min CSP gamma. Actually, this is, in general, if you look at the literature, it's not called min CSP, it's called valued CSP or VCSP. Just because, I mean, if these things only take values like say 0 and 1 or something, so then it counts the number of unsatisfied things, but in general it could take arbitrary values. So this is a more general problem. So VCSP, so let's talk about VCSP. This is tractable if and only if gamma, which is now a collection of these functions, has a non-trivial fractional polymorphism. Okay, and in fact in this case non-trivial is something very, very simple, which is arity 2 and symmetric. I need to tell you a little bit what fractional polymorphism is. I won't define it very precisely, but I'll give you a flavor. And this is arity 2 symmetric. So in this case there is an algorithm, and in fact tractable via a basic LP. So that linear program I wrote last time to test for satisfiability, it's fairly obvious how to extend it to solve this optimization version as well. Okay, you just put, we just said that every constraint had to be satisfied. Instead, you look for all fractional assignments and you simply take the expected contribution to pi under that fractional assignment for each thing. Okay, so it's just, you can think about it, it's a simple exercise to extend the LP to relax this optimization version. And there are, so a particular collection of these things will be tractable if and only if that LP solves. Basically, in some sense, this is very nice. It says that there is a canonical algorithm, a very simple algorithm, and either it works or the problem is NP hard. Okay, so this result is it built up on a few works, but the final form is by Thapar and Zivny, I think 2012. So it's now about, and I think the journal version is like 2016 or something. Okay, so it's some very nice result in the last 5 years. And in some sense, this was easier than the CSP dichotomy because life is tough here. So most of the time, the problem is hard because you're asking, I want the exact optimum of an optimization problem. You would think that most of the time this is hard. Even if you take something like 2SAT, 2CNF, the decision version is easy. But if I ask you minimize the number of unsatisfied 2SAT clauses, that becomes hard. Okay, so most of the problems are hard, and that's why this is sort of easy. Most of the problems you don't have to worry about, and pretty much the only reason something is easy is a fairly simple algorithm works. Okay, and what is this fractional polymorphism business? So here you're talking about things taking values. So fractional polymorphism is nothing but a distribution. So I'll just give an intuitive feeling, and maybe you can look at the paper, or the scribe can include the exact definition. So it's basically a distribution on polymorphisms. Okay, so and the point is, if I give you a collection of assignments, then if you draw a random polymorphism from this distribution and apply it, its value will be smaller than this. Okay, so I'll just give an example. So for example, one thing you might say is that, so, and the polymorphism is with respect to a function now. So for example, you might write something like P, and if you want, I can, okay, let's keep it as P. So when are you a fractional polymorphism with respect to this? Okay, let me just write down. So I only talk about arity 2. So I only have to talk about two things. So I take two assignments A and B. So expectation of G in omega of this is at most P of A. So what have I written here? Suppose I take two assignments A and B in D to the K. Okay, and then P is something which maps D to the K to this thing. So it says that if I take two assignments, I got a certain average value here. If I take a random polymorphism and apply G to that, I'll get a new value in D to the K. If I now take P on that, sorry, what is F here? F shouldn't be there. So, okay, if I now apply P to that, that will be smaller than this average value. So basically, these polymorphisms give you a way to improve the solution quality. Okay, and this is a special case when the arity is 2. In general, you will have whatever arity you have, and then suppose the arity was m, you will have m things here and m things there, and you will put 1 over m. The arity 2 is actually very nice because there is one, and this omega is basically a distribution on functions, so distribution on functions from d squared to d, because now I'm talking about arity 2 functions. And one particular case which is a very important, and this really, which this generalizes, is this notion of submodularity. So you can actually take these two functions to be and or. So you can, if I just write something like this, A and B plus P of A or B. Okay, so I can cancel the half. So this is basically submodularity. So if your functions are all submodular, you will get an algorithm to minimize this thing, and that's just, falls in this framework. Okay. So this is basically a collection of functions such that a random one of them allows you to improve.
I didn't understand for that last one. So if all the constraints are
so for example, all the constraints are submodular like this. Yeah.
Then it is always tractable.
It is tractable.
Giving the
Yeah.
out.
Yeah.
And that is via the basic.
Yeah, and this is for the Boolean domain. So you'll have to again generalize these things to larger domains. And the correct thing is basically you have some arity 2, and also symmetric simply means that G of AB is equal to G of BA. Okay, which I guess and or are. Okay, so this is submodular. And again, this is just to give you some perspective that you can really capture optimization also in this framework. Yes, question?
Distribution on all functions?
No, yeah, it's all functions, but here the support is only on two functions. So it's in general distribution on all arity 2 functions from d squared to d. But here there are only two functions I talk about.
The distribution only is polymorphism.
It's a distribution on functions, yeah.
But in the previous case, you take only distribution on symmetric functions.
Yes. Sorry, what is the previous case?
That case, if you have a...
Yeah, so I'm just saying, so in general, omega is a fractional polymorphism if this holds for all A and B. So omega is a sort of arity 2 fractional polymorphism if this holds. And then this theorem, so this I should say is a major theorem, it says that a CSP is tractable if and only if gamma admits an omega which is symmetric.
Omega is symmetric means the support is on symmetric.
Yes, okay, so good. I should have said, what does omega symmetric mean? Support, everything in its support is symmetric. Okay, let's write it down. So it's a definition for all G in support of omega, G is symmetric. Okay, so this is a theorem of Tapar-Zivni.
So if something has non-zero support in omega, does it mean that for the corresponding decision version it is a polymorphism in the old definition?
So I see. I think that might. So if you have P to take 0, 1 values, then it must be, right? So for example, if P was a function from D to the K to 0, 1, where it is 0 if it is satisfied and 1 otherwise, then if A and B both send you to 0, then everybody here must be a polymorphism. So indeed you're right. So if you're trying, so if you're 0, 1 valued, if P's are still just predicates and you're counting the number of unsatisfied assignments, then to have to have a fractional polymorphism, you must be entirely supported on regular polymorphisms. You have to be.
But in general, when P assigns values to tuples,
Yeah.
fractional polymorphisms is, I mean, normal polymorphisms don't make sense, no?
Yes, yes. So it can be anything, but the condition you need to satisfy is this. So this will be a fairly stringent condition as we observed that if P is a predicate, then in particular anything in the support has to be a polymorphism as we saw it before. Because the right hand side becomes 0, so the left hand side has to be 0. Okay, great question. So in some sense this generalizes that theory. So at least for predicates, you can only be solvable for the optimization version if you had were solvable for decision version, but actually much more. The only way you can be solvable in the optimization version is that you simply have an arity 2 symmetric polymorphism. Okay. And using this you can say what all Boolean problems are tractable and so on, and that was long known, but now we have a complete theory. Okay, and this whole thing is not hard. So I mean these two papers, there are two papers. The first paper said that a basic LP will work if and only, if and only if this arity 2 symmetric existed, and then the second paper by Thapar Zivny said if you didn't have this, then you're somehow hard. It reduced like max cut or something to it.
You need every G in omega to be symmetric.
Yes.
Or is it enough the expectations?
No, every G. So the support, so symmetry is here is just as a function on, as a discrete function. So you should be entirely supported on symmetric things. Okay, that's the criteria. All right, so that was optimization. So let's also briefly talk about approximation. So let's do that here. And here for some reason I'll talk about max CSP just because the community tends to focus on this. So I give you a collection of constraints. I want to maximize the number of satisfied constraints. Or I might have weights and I want to maximize the total weight of satisfied constraints. Okay. So here I won't define all these things, but basically here it's known that the so here it's a little bit tricky because there's a whole range of approximation factors. If you take max cut, if you want to approximate it within like 0.878, we can do it. Within 0.99, we know it's not possible. There's some intermediate range where things are open. So here what we are going to ask is, I give you, so let me just say you're given a collection of constraints. So maximize the number of satisfied ones. Okay. And then we are interested in the best possible approximation factor. So say we want solution satisfying at least alpha times opt, where alpha is the approximation factor. Okay, so opt is the best anybody can do, and you would like to find something which is at least alpha times opt. Okay, so here I'll say the best possible approx ratio alpha is governed by something called low influence approximate polymorphisms. So I won't define these, but there is an appropriate notion of polymorphisms you can define. And so now you have to get quantitative. So far we have talked about non-triviality in terms of structure of the polymorphism, like it is symmetric. So somehow non-trivial should mean that it's not dictatorial, right? And symmetric is the extreme when you treat all variables equal. So for example, in the optimization case, symmetry is needed to get an algorithm. So here you can't quite say something that strong, but you say symmetry by saying that no variable should have any undue influence. So low influence means that no single variable has too much influence on the polymorphism. And again, influence is a technical notion from analysis of Boolean functions, which is plays an important role in many parts, including approximation. Okay, but there is a very natural definition of what the influence of any variable is on the output of the function. And if every variable has low influence, then it's somehow a polymorphism which doesn't favor any variable too much. So if we have such a polymorphism, and it has a polymorphism itself has some sort of approximation guarantee to it. Okay, in just one sentence it will say that if I sample a bunch of, if I have a distribution where I sample assignments and it satisfies the constraint with some probability p, if I apply the polymorphism, it should now satisfy the constraint with probability at least alpha times p. So it should hurt the probability that you satisfy the constraint by sort of an alpha factor. And that alpha will exactly govern this particular thing. Okay, and just a comment, I'll give more, just a reference here if you want to think. So the algorithm is SDP. So basically the SDP, standard SDP works. Standard semi-definite.
That alpha is the best approximation.
Yeah. Okay, I'll come to the best part thing. Standard semi-definite program will achieves. So let's say it's alpha approximate polymorphism, even though I didn't define it. So achieves alpha approximation. Okay, and this is a result of Raghavendra generalizing some previous works on max cut and so on from 08, about 10 years now. And so this gives the algorithmic part, it's unconditional. So once again, if you have rich enough structure of polymorphisms, you can get an algorithm. Now the algorithm is a little more complex because you have to use semi-definite programming and rather than linear programming. But it is one canonical algorithm, which just you write down for any CSP, that's the thing. And then the hardness, the fact that you cannot do better is conditioned on the unique games conjecture. Which is something you might have heard about. I defined the unique games problem in the first lecture. There is an optimization version of this. So for the unique games, it was from our CSP satisfiability viewpoint, it was an easy problem. You could always tell if a UG instance was satisfiable. But what if I gave you an instance which is not satisfiable, which is only 1 minus epsilon satisfiable? Then it turns out there is no known algorithm which can even satisfy like 1% of the constraints. And the unique game conjecture basically says that's indeed the problem is hard. You cannot find such an algorithm. And if you assume that, basically that's essentially, it's equivalent to assuming that polymorphisms are the end of the story here. There's no way to go better than polymorphisms. Okay, so in that sense, also even in approximation, we have a satisfactory understanding based on polymorphism. Okay, any questions? Sorry, I'm not more precise on any of these. I can give more details offline if needed, or Rajit can fill in some details, or at least the definitions. And these definitions are not too, I mean, this definition wasn't bad. This definition is a little bit more tricky. You have to develop the notion of influence and all that. But
the unique games conjecture turns out to be false.
Mm-hmm.
So, what all lies in between?
So if the conjecture is false, then probably that means that there's an algorithm better than the semi-definite. I mean, it's equivalent to the fact by this, what I said, that there is an algorithm which does better than semi-definite programming, at least the basic semi-definite programming. And which is definitely possible. So even for something as simple as max cut, we can write down a fairly simple semi-definite program, and that could be. Sorry?
But this is just saying that if UGC is true, then it is hard.
If UGC is true,
Then the SDP gives the best.
right.
If
Right.
UGC is false, it's not implying anything.
If UGC, well, one thing is that the UGC itself is a constraint satisfaction problem. So if you believe the qualitative form of unique games conjecture, there is a certain quantitative form which will also it will imply. Yeah, yeah, right. And then that algorithm must be improvable. And therefore, yeah, so you're right. It's not sort of just like a contrapposto or anything, but it's true because UG itself is a CSP. So that statement that believing the UG is basically just believing that no better program exists. And the point is, there is even you can strengthen the semi-definite program in a fairly minimal way, and even that could potentially refute unique games. We just don't know. Because I said this is just the standard semi-definite program. You can imagine adding more strong constraints. And we know that such constraints for, say, the LP do not help in the optimization version, but perhaps they do help in the approximation version. We don't know. Okay, so. All right, so. Any other questions?
So by hardness, you mean improving the alpha.
Yes, yes. So hardness would mean that getting an alpha plus epsilon approximation for any epsilon would be as hard as refuting the unique games conjecture. So if you believe this is NP hard, you'll get NP hard.
Something like the Aurora-Starrett algorithm for unique games, does it work for that general?
Right. So that's a great question. So it's not known. Yeah. So Arvind's question was there is for unique games, one of the reasons it's maybe a somewhat peculiar problem is that it's false if you allow runtime like 2 to the n to the epsilon. So if you allow runtime like 2 to the n to the 0.1, then the conjecture is false. Whereas a lot of other things like SAT and so on, we don't have any algorithm running in 2 to the little o of n time. So this problem has some weakness in it. But using that, you can now ask, can I do alpha plus epsilon approximation in something like 2 to the, or anything, or 2 to the root n. Say if you take max cut, for which you might have heard of the Comans-Williamson algorithm, which achieves 0.878, can I beat that by epsilon, some positive epsilon, in 2 to the root n time? We don't know. Some of the reduction, because we are reducing unique games to that problem, we don't have any, pretty much we have no connection going the opposite direction. So we don't have any unique games completeness results. So, which is also why you could get an algorithm for unique games and leave empty-handed with no algorithms for other problems like vertex cover or max cut or other things. But it seems unlikely, because the way you will probably do better is by getting some understanding of semi-definite programming beyond this, and odds are that will help with other problems as well. But formally, yeah, you could just solve that and get nothing else out of it. Okay. Any other questions, comments? Okay, so now the last part I want to talk about is probably closer to home here, so I wanted to include that. It's on fine-grained connections. So I'll do this, and then I'll finally talk about promised CSPs, which is what I originally promised to discuss. So now you focus on NP-hard CSPs. Okay, so most CSPs are hard, so what do? We have to deal with these. So now what we would want to understand is, so you want to understand the variation in best exponent of fast exponential algorithms for various CSPs. For example, so Y is 10 SAT, apparently harder than 3 SAT. So what do I mean by this? So you can take the world record algorithm for 10 SAT, and that will run in time C10 to the n. Okay, and I believe that will be 1.8 for this, because it's 2 minus 2 over k for k SAT for largish k, and I hope 10 is large enough. So somebody more informed can correct me otherwise. And then you have C3 to the n, and C3 is, so this is the best runtime for this, and this C3 is certainly known to be less than 4/3. Okay, so you might have seen this famous 4/3 to the n Schoning's algorithm. And here I'm sort of not distinguishing too much between randomized and deterministic, though for specific problems there sometimes is a difference, and it's quite non-trivial to match the performance of randomized algorithms. Okay, so now we would like to understand, okay, why is this? Why is C10, so is C10 more than C3? So again, what is the definition here? I should also say there's something called the exponential time hypothesis, which implies C3 is positive. Okay. So this is obviously strong, and again, not positive, more than 1. So sometimes I write it as 2 to the alpha n, and so, right. So C3 is more than 1. What do I mean by that? So this is exponential time hypothesis basically implies that 3 SAT requires 2 to the omega n time. So in particular, you can't get a 1 plus epsilon to the n algorithm for arbitrarily small epsilon. Okay, that's a stronger form. Note that in particular implies NP is not equal to P, but people believe that not only is 3 sat not in P, it actually requires like genuinely exponential time. We don't have a 2 to the little o of n algorithm. So the ETH implies the C3 is more than 1. On the other hand, there is an upper bound, so you might want to understand what is the value of C3, which is the smallest value for which you have a C3 to the n algorithm. And the current known values support the fact that C10 may be more than C3, though there is no condition ETH or not under which this is known. Okay, so we don't know this. Again, in terms of like challenges I find very interesting, broadly is that we don't know this. So we also don't know is that can you give some epsilon naught positive, some absolute constants such that C 10,000 is more than 1 plus epsilon naught. This is also not known. So ETH says that C3 itself is more than 1, but we don't know. It could all be like really, really close to 1. So we don't know these things. Again, these are not related. Just wanted to throw out these two questions. Okay. So we don't know any explicit lower bound assuming ETH on this. So we don't know that C1000 is at least 1.00001. Okay, we can't show those things. And which is also very peculiar because, and for this I'm even allowing a stronger form of assumption called, again I'm digressing here a little bit, but maybe it's probably good to give these things. There's something called strong exponential time hypothesis, which says that for all epsilon, or let me say for all eta, there exists k such that ck is more than 2 minus eta. So it basically says that as you increase k sat becomes harder and harder, and in the limit you only have a 2 to the n algorithm. Okay, this is strong exponential time hypothesis. So we know that in the limit you will go hit 2. So even if you make that assumption, we don't know if at 10,000 you even leave 1 barely. We can't show such things. Okay. But okay, what does all this have to do with polymorphisms? So I found this very neat paper in Soda a few years back. So I want to just discuss some of the things they proved, and also there is a very nice theory of polymorphisms which can potentially explain this. So the ultimate dream here would be that not only is these polymorphisms going to tell you are you in P or not, which for CSPs they have now done, but sometimes they might fall short of putting the problem in P, but there might still be some non-trivial polymorphisms which I'm going to define in this framework, and just the richness of them maybe is fine-grained enough to tell you what the exponent is. So you could imagine this very pleasing theory that you give me polymorphisms, I look at its structure, and based on that there is going to be this exponent, and if that structure is rich enough, that exponent will converge to 1. It's like an infinite family of polymorphisms, it converges to 1 and then get a polynomial time algorithm. Okay, or at least sub-exponential time algorithm. So that there is, obviously that's a very bold hope, but maybe someday we'll have such an understanding, at least for CSP. So there is this paper of these 4 guys, Lagerquist, Nord, and Zanuti, 14 I believe, Soda 14. So they used partial polymorphisms, and I'm going to define these in a second, to study fine-grained exponential time complexity. And actually I should also credit this earlier paper which they lean on. They mostly used this paper's ideas and then put it together in a nice way by Schnur and Schnur. Okay, so what is partial polymorphism? Okay, so these are known to basically I'm going to define now what partial polymorphisms are, and I'm going to state a Galois connection which says that if you care about the exponent of the best exponential time algorithm for a CSP, just look at its partial polymorphisms. That's got all the information. You may not be able to tame that information and get your answers, but it's there somehow. So what's a partial polymorphism? Well, it's just a partial polymorphism, that's all. It's a polymorphism. What is a polymorphism? It's a function. So what was a polymorphism? It was a function from d to the k to d. So now a partial polymorphism is something which will be undefined on some, it's a partial function, which on places it is defined behaves like a polymorphism. Okay, you can define it as a partial function, but let me just for convenience say that I extend the range by 1, so on some inputs it can bottom out, so it can output bottom. And now once again, so let me use m here and use k for the arity. So suppose I have x11 to x, so how did we define polymorphism? So again I'm going to define f is in p pol of some particular relation p, so p is a subset of d to the k. Then if I basically take m such rows in P and I apply f column wise, I should get something in P. Okay, that was the definition. But now a partial polymorphism may not be defined on some of these columns. So if a partial function is a partial polymorphism for a relation P, if whenever it is defined on all the columns, the output must belong to P. So again, if you take m tuples in P, apply f column wise, two things must happen. Either you're undefined on some column and then all you can go home, there's no requirement. Or if you're defined on every column, then you should be in the predicate P. That's a partial polymorphism. So obviously a regular polymorphism is a partial polymorphism, but this basically allows you to be not defined in some cases, and this makes, so such partial polymorphisms obviously always exist, so you can be undefined everywhere, and so you're now a partial polymorphism for everything. And somehow the idea is that the more partial polymorphisms you have, in some sense the less hard you are. You're all NP hard once you don't have a polymorphism, but you are less hard in the sense that your exponent will be smaller. Okay, so what do I, so here is the Galois connection, and okay, this is for a particular predicate, and then p pol of some collection of predicates gamma is of course just going to be the intersection of p pol of all the predicates in that constraint language, okay, as before. So now I can take two constraint languages, gamma and lambda, and I can ask, if one has more partial polymorphisms, what does that imply? So the Galois connection here, and we have more or less done the proof, and I think this may be a good way for you to sort of recollect that thing, so you can go over that proof and just try to prove this particular thing. So p pol, so if you have more, so I think I'm consistent in lambda and gamma here. So if and only if lambda implements gamma without pp implements, without auxiliary variables. Okay, so in particular, which of course implies that CSP of gamma reduces to CSP of lambda, but in a very nice way, with no new variables. Okay, or maybe you introduce one or two variables, but it doesn't, So. And why is this interesting? Because now if you have a runtime of C lambda to the n here, right? If you have, now this is, lambda is also an NP hard problem, so it will have some exponential time algorithm. Suppose it has a C sub lambda to the n algorithm. Then this will also have a C sub lambda to the n algorithm. Because given an instance, you can reduce it to this. You haven't introduced any new variables, and so the exponent will have to remain the same. So in particular, this implies also that C gamma is less than or equal to C lambda. Am I saying it correct? Yeah. So again, if you have more polymorphisms, it should be easier. So that's the reversal. So now you're easier. So earlier we just said that if you have, for polymorphisms, the question was whether this was one or not in some sense, whether you had a polynomial time algorithm. but it's actually more fine-grained. Once you allow partial polymorphisms, the connection is fine-grained enough to say this. Okay, so that's the. And now it is true that you can check that 10-sat will have fewer partial polymorphisms than 3-sat. I'll actually tell you what partial polymorphisms of k-sat look like, or at least some of them. So it then stands to reason that 3-sat is not any harder than 10-sat. Okay. Which is not that difficult. You don't need all this theory to see that. You can reduce a 3-sat constraint to a collection of 10-sat constraints using some fixed global auxiliary variables. That's not a problem. But this is the broader theory explaining all that. Okay. So, all right. So let's see. What else did I want to say? Okay. So using this, what these guys, so they studied this thing and they said, so now you can order all these NP-hard problems based on this, these partial polymorphisms. So they call these things partial clones. So basically these partial polymorphisms. And what these guys did, the JLNZ paper, is that they took all Boolean CSPs and they studied the relationship between these exponents. And one thing they basically said, so that paper JLNZ 14 said that they identified the easiest NP complete Boolean CSP. So what do I mean by that? The easiest, I mean it's the problem for which the corresponding exponent is the minimum. We don't know what that value is. ETH will assert that value is bounded away from 1, but we can say that any other CSP will have an exponent not smaller than this. Okay? And in fact, it is CSP of this particular relation R. So it's just a single relation. And R is a subset of 0, 1 to the 6. And it just contains just 3 things. So there is, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, and 0, 0, 1, 1, 1, 0. It has these 3 6 tuples. And this has the smallest. They can prove that this has the smallest thing. Yes, so what is this thing? It looks strange. How did I write it up without, not from memory, but the point is this is 1 in 3 sat. And then you just add some more variables which are just going to be the opposite of this. Okay, for some reason this maybe affects the exponent by square root or something. So this is basically 1 in 3 sat. So somehow morally you can remember 1 in 3 sat is the, plus some flips, okay, which makes the additive 6. Okay, and 1 in 3 sat is actually pretty easy. I don't know how these algorithms work, but the best runtime is 1.09 to the n or something. So it's actually pretty fast. Algorithms exist for 1 in 3 sat. I'll go exists. Okay, so I just wanted to throw this out there that this is a very nice theory also in fine-grained connections. And depending on time, I might talk about some of our contributions to this fine-grained thing. And again, the principle here would be that we saw that rich enough polymorphisms give you polynomial time algorithms. So now what we can do is try to take somewhat principled approach to these fast exponential algorithms, which is a very rich and burgeoning subject, and say if you give me some rich enough partial polymorphisms, I don't need to know anything else about your constraints. I'll just use these polymorphisms to give you an algorithm which beats brute force. So I think this is seems like an interesting direction to me, and we have one such instance. So what is the partial polymorphism of k-sat? So I'll just tell you how partial, because I haven't really given you any examples. So let me talk about p-pol of k-sat. Okay. And it's actually very simple. So I have a polymorphism from 0, 1 to the m. So I'll define what m-ary polymorphisms are. And I allow you to bottom out. And it's simply a threshold function. is 0 if the Hamming weight of thing is less than m over k. Okay, assume k does not divide m, so simplicity. It's undefined and it's going to be 1 for the high Hamming weights. Otherwise. So if you look at the hypercube picture, so you're 0 here, you're 1 here, and you're undefined in the middle. So you can check that this will be a partial polymorphism. So we'll do the check, it's simple. And now you see why, say, 3-sat has, in some sense, a richer partial polymorphism, because it's a less partial polymorphism, because it is defined for 2-sat, 3-sat, you will be defined on 2/3 of the domain, whereas for 10-sat you're only defined on 1/5 of the domain, like 1/10 here, 1/10 there. Okay, and why is this a partial polymorphism? So let's just see. Probably some of you see an even slicker way to do this. So you have m of these assignments, and they're all satisfying assignments for k-sat. So which means there is at least 1 somewhere here. Of course, there can be negations, but everything is symmetric. So let's just assume there are no negations. So let's say it's a monotone clause. So there is at least 1 here, which means if you count the total number of ones, there are at least m ones. Which means there must be a column with at least m over k things. Okay. So of course you could be undefined somewhere, but if you're undefined, you're off the hook. So if you ever get a bottom here, you're off the hook. The only worry is that you output all zeros. But you can't do that because there are m of these ones, and so there must be one of the columns where you at least have m over k ones. Okay, and the part with negations is the same thing. Basically, for each column, it's more important to have a 1 or a 0. So you just take that and then you count that. So there must be a correct column with the correct. Okay. So this is why it's. So again, maybe I should repeat this. So again, I want to check that this is a partial polymorphism. So let me take m satisfying assignments to k-sat. Let me assume the constraint is just x1 or x2 to xk. So satisfying assignment means that there's at least 1 somewhere in each of these rows, which means there is a total of m rows across m ones across all rows, which means there must be a column with at least m over k ones, and then that will output this. And I assume k doesn't divide m, so then if it's at least m over k, it will be more than m over k. It will work. Okay. Oh.
That's fine. You'll produce
Right. So I'm just saying that for you to be all zeros, I think Saket is right. Let me clarify this. So when are you not a partial polymorphism? If I can find m such things for which you output all zeros, because if you output any bottom or any one, you're home free. But if you output all zeros, which meant that each of these has less than m over k, which means the total will be at less than m, which is a contradiction. Okay, is everyone good with that? I mean, just the same style of argument. So this is a partial polymorphism. And now I'll state one general result we have.
This is the entire collection of.
Okay, that I don't know. Probably not, because you can still do things like compositions and other things. So the actual things are probably richer than this. Yeah, and actually that's also why this theory might. It's unclear how much about polymorphisms. If you want the best algorithm for k-sat, maybe you should really study k-sat, because it might have some richer structure than something which only has these polymorphisms. So it maybe doesn't matter for polynomial time because it's a coarse enough notion, but once you study something this fine-grained, maybe the fastest algorithm for k-sat should do something with these things. But the nice thing is for k-sat, at least for large k, we can use this general framework to get an algorithm matching the best thing, but for 3-sat there are better algorithms. So I'll tell you briefly what I mean by that. So, okay. So we have a general result saying that here is sort of a meta theorem. I mean, again, this is with Josh. It's not yet written. I mean, it's written but not posted, I guess. So suppose you have partial. So basically, it says that rich enough partial poly implies fast enough exponential algorithm. Okay, so in the spirit of polymorphisms governing algorithm. So what do I mean by this? Suppose I'm going to have a sequence. So I'll assume the assumption is always I'm going to make some assumption on what polymorphisms I have, which will sort of generalize from this K-SAT instance and then give an algorithm. So assume we have a sequence of symmetric polymorphisms such that some Fm of increasing arity, such that Fm of x is defined on some subset of the Hamming weights. Is defined. So, and then let E be some subset of 0, 1, and let's say it's union of some closed intervals. Okay. Suppose it's defined if the Hamming weight of x by m belongs to E and undefined otherwise. Okay. So then that implies we can get, and again this is for a Boolean CSP. Suppose then we can get a 2 minus measure of E to the n algorithm. Okay, let me throw in a little of n on top there. So if I have a sequence of symmetric polymorphisms, which are somehow basically, so they are symmetric, so they only depend on the Hamming weight. So let's just draw that picture again. So if you have some hypercube like this, and maybe there are bands here which is 0, there is a band here where it's a 1, there's a band here where it's a 0, and the rest of the places it's undefined, let's say. You can give me any sort of crazy sequence of functions like this, you know, and if there is some CSP for which it is a partial polymorphism, all of these, so we just need an infinite sequence of these. Then we can beat the brute force by an amount which is sort of I mean, maybe there will be even better algorithms perhaps, but we can at least do this. So the more you are defined on, the faster my algorithm will be. And note that for K-SAT, this E is this bottom 1 over K and top 1 over K. So the measure as in the standard topology of 0, 1 is 2 over K. So then you get 2 minus 2 over K to the n for K-SAT, which is the best known algorithm. I should say that we can get randomized. So this is a randomized algorithm based on random walks, and it has some similarities to Schoning's algorithm. So you might, this is a famous algorithm of Schoning, very simple for K-SAT, which is randomized, and we match that runtime. But some of you only use the fact that you have polymorphisms.
Might be like closed intervals. That's not important. Well, but there you have open intervals.
There I have open intervals. So what you will do is you'll take something. Yeah.
I mean, it matters in.
It doesn't. I mean, it's not so important. I think. Yeah. It's just that if you have isolated points, then. Yeah, it's sort of without loss of generality, let's say. Yeah, because you can always take a closed interval which is slightly smaller than the open one you care about.
You don't want point intervals.
Yeah, so if you have point, you should want to throw it out. That's why. Yeah. So you want some sort of, just for complexity reasons, you just want some finite number of. In general, any closed set will be fine, but your runtime of this algorithm will depend on the number of those intervals. Right. Yeah. So that's why I said closed, because if you're open, it might take lots and lots of intervals to cover that, and then that might be a problem. Okay, so that's that. So, and I'll also state the way we do it.
So this is only for Boolean.
This is only for Boolean. We have only studied Boolean so far. Yeah. So and actually the way we do this has got not much to do with CSPs actually. It's really about optimization. So suppose I give you a linear program. So AX less or equal to B, and I tell you it's feasible over X in 0, 1 to the n. So as a 0, 1 integer program, it's feasible. Okay? And now my goal is basically to solve this. Obviously, then it's going to be an NP-hard problem to solve it. Okay? So now the question is, so I take some E which contains 0, 1 and is contained in 0, 1. And this is this exact union of intervals. And now my goal is to find a solution which lies in E. So find a feasible point for LP in E to the n. So this is like a promise problem. Okay. So this is the problem. And what we can do is for this, we can give an algorithm which runs in 2 minus measure of E to the n. To the n plus little of.
What is the promise is that it is feasible over 0?
0, 1 to the n, yeah.
That is integer.
Yeah, the integers, yeah. 0, 1, yeah.
Can you chop up the cube into so many fractional LPs?
Yeah. So note that this runtime doesn't depend on how many pieces of E contains. I mean, there might be something that, but it'll depend polynomially on that. Yeah. So, yeah, you can't brute force, right? Because E itself is, there are lots of rational points there. So, but somehow the algorithm has that flavor. Actually, the point is you sort of onto something in the sense, if I tell you which interval in E I need to find something in, then that's something I can do. Because the problem is that here it's a union of intervals. If I gave you only one interval, then it's a linear constraint. So somehow the algorithm has this point where it tries to guess which one of these, say E is a union of some L intervals. Yeah, and then it says, oh, I'm wrong. So I'll flip the interval to which xi belongs in each step, and then and it has to make that choice carefully based on some random walk. There is some min-max theory and so on to make this thing. But then this is what it in the end does. Okay, so if I have time, maybe in the last lecture, if there is interest, I can pretty much focus on this and present the algorithm. So it can be presented in more or less than one lecture. It's just elementary, a combination of various elementary things in some careful way to get this things. But it seems to have not been known before, and it seems to me something very natural. I have an LP which is feasible over the hypercube, and of course, if I take E to be the full interval 0, 1, then it is polynomial time. So this is like an interpolation. So this basically interpolates between IP and LP, right? And the more permissive I am, the faster I can give you an algorithm. And why does this imply a K-SAT algorithm? So it actually, using this and some theory of polymorphisms I'm going to tell about, this just pretty much comes immediately. But just to give you a glimpse of it in a very concrete case, so how will you write 3-SAT things? So suppose 3-SAT, you might have variables x1 to xn. So if I have a class x2, what's the standard LP? So you'll say if I have a class x2 or x3 or x7, 5, you will say x2 plus x3 plus x5 is at least 1. Right? And if you have negations, you will say 1 minus x3 plus x4 plus 1 minus x7 is at least 1, and so on and so forth. A collection of 3 CNF classes I can write as a collection of inequalities like this. Basically saying at least one of the literals is true in every class. And this being feasible over the hypercube is exactly the same as the 3 sat instance being satisfiable. Okay? But now I can take, so now I can find a solution. Suppose I can find a solution in 0, 1/3 to the n, 0, 1/3 union 2/3 1 to the n, where every variable, so basically I know there is a 0, 1 solution, but I just ask you to find, and of course finding that is hard, but I want you to find a solution which is not too far away from the boundaries. So which always lies in the first 1/3 or in the last 1/3. So you're not allowed to use this. Okay, note that here I'm this is not a closed interval, but it doesn't matter. We can take a closed interval which is slightly smaller than that, and that will only affect the runtime slightly. And why is this good? Suppose you found a solution like this, then how will I convert it to a Boolean solution? Just round things on the lower side to 0, things on the higher side to 1. And the point is, if I take a constraint like this, okay, and it's with, the negations can be handled similarly. If I have a constraint like this, not all the 3 variables can be less than 1/3. So you must have had something which falls in the other range, and you would have put it to 1. Right? So that's the entire algorithm. Once you have that, you get this thing. And what is the runtime of this? Now it's 2 minus 2/3 to the n, which is 4/3 to the n. Okay. All right. So that's what I wanted to say about that. And for large K, the nice thing is this matches the best. This very general algorithm, which only uses some particular polymorphism about K sat, matches the best known algorithm. So you didn't need to know anything more. All right. So any questions?
The connection between so when P is not just 2 extreme intervals but many pieces, how does this help you solve this underlying CSP, which has all these polymorphisms?
Yeah, so then the rounding algorithm, okay, so very briefly we'll basically write the same canonical LP we wrote last time, right? And then we will try to find a solution for that, but then we will be guaranteed that each variable will not now get value 0 or 1, it will get some value in 0, 1, the interval. But because I can find a solution, that LP will be feasible by my promise. But then I'll find a solution where each variable only lies in the range in E. Then my rounding function will simply take my polymorphism and apply it. Because it's now in E, the partial polymorphism will be defined. So I can actually round my solution. Very similar to here. I was able to round, if I got somebody at half here, I wouldn't have known what to do. But because I got...
so these polymorphisms will allow you to...
Yeah, but the polymorphisms are defined in E, so I just make sure I give you a solution which the polymorphism can round, which polymorphism can make sense of. And briefly for 2 sat, for example, majority is a polymorphism. So modulo some, so basically what you'll write the standard LP, and if you get value more than half, you'll say it's 1. If you get value less than half, you'll say it's 0. There's a slight issue that you might get value exactly 1/2, so that's something you have to handle. Okay, so you have to avoid some boundaries, but modulo that's why that's the 2 sat algorithm. Take LP plus majority rounding, and that was well defined because the majority is defined on all the Hamming weights. But now you're only defined on some subset of Hamming weights, intervals of Hamming weights. So there you can apply the polymorphism. So you find a solution which lies there, and then you just round. Which is exactly what happened here. So you found a solution in this. The polymorphism was, we just did threshold rounding, but the polymorphism also said that in this region you output 0, in this region you output 1, and in between you're undefined. Okay. Any other questions? So I guess we are halfway into lectures, so now I can now actually define promise CSP, which is.
So instead of only one union of those intervals, we have n intervals, E1 up to En, and I want a feasible point in this E1, E2.
Yeah, so that's a good question. We haven't formally checked that, but I feel like product thing we can handle fairly easily, I think. But a more interesting question will be that what if E is just any closed set? So for example, you could take some point in the hypercube and, for example, your E could be take the hypercube and take all the points within some within some Euclidean distance of all the corner points. Take the union of those balls. Can we handle such things? I don't know. So non-product sets will be more tricky to handle. I feel like whether it is E to the n or E1 cross E2 cross E3 should not matter so much. Though strictly speaking, we haven't checked that, but I suspect there won't be any major problems. The non-product case will require additional work. Yeah, but that's right. So in general, you just want some arbitrary closed set here, and then you want an algorithm which relates to that measure. So maybe the complement of that or something like that. So the more things you define now, the faster the algorithm should be. Okay, so maybe so now let me do. Any other questions? Sort of bad to start something new in the last 15 minutes, but it'll be light. It'll only be definitions and examples, so we won't do anything fancy. So I'll talk about promise CSP. Somehow it's actually working on these which got me interested in all these business. And this has a very nice connection to approximation. Also, there's a very canonical tough net problem. So I'll start with that and then I'll define. So suppose I give you a graph which is 3 colorable. Can you 10 color it? So this is a problem which we do not know to be in P or NP hard. Under some strong enough variance of UG-like problems, this is known to be hard, but we would like to sort of understand what's going on. Can we prove this is hard? And of course, I strongly bet this is NP hard. Okay, so this is something we don't know. We do know that you cannot 4-color it efficiently. So given a 3-color graph, you cannot 3-color it efficiently is 70s, right? So you can also not 4-color it efficiently. That we have known for 20 years now. Just as of this month or so back, using all this polymorphism theory which extended to promise CSPs, which I'll tell you about, researchers have shown that 3 versus 5 is hard. So you can't 5-color also, which is quite an impressive thing. We didn't know how to do that for a long time, and now it's maybe hints at why we didn't know all this, because we needed to maybe think in these algebraic terms. We are missing some of this language. But what kind of problem is this? So what am I doing more generally here is that, so 3 coloring is a CSP. As I said, it just had a single relation. Gamma was like not equal, and not equal was just equal to A comma B, A not equal to B, and A, B in 3. Okay. So that telling if you are satisfiable for that was hard. And now let me just define it as not only 3. But now what does 10 coloring? It is the same thing. But now I allow A and B to be in 10, 1 through 10. So clearly this relation contains this relation. So what I'm asking here is that I'm giving you 2 relations, and I'm telling you you're satisfiable according to one of them, the more stricter one of them, but I only ask you to satisfy it according to the more permissive relation. So that's what promise CSP is going to do. And so in general, it's going to take not just one relation, but a finite collection of one set of relations and another finite collection of relations. And then, and somehow, the former will always be stricter than the latter. And then I'll ask you, are you satisfiable according to the strict one, or not even satisfiable according to the stronger one? So let me define that formula. So suppose A. So and again, I'll do this slightly more generally, just to allow to talk about some other problems as well. Things, and I'll give you some examples. So suppose A is set of relations over some domain D, okay, and then B is this set of relations over E. And now these have matching arities. So that's important. So what do I mean by that? So A may be some P1 to P, some L. And then B, and these are like an indexed collection of relations, Q1 through QL. And the Pi and Qi must have the same arity. And all the Pi's are defined over D, all the Qi's are defined over E. Okay? And I need one more condition. Okay, continuing, such that there exists homomorphism, there exists a phi from D to E such that phi of Pi is contained in Qi for all I. So basically these are homomorphisms from relation Pi to Q. So this is my hypothesis. So I give you a collection of, some finite collection of relations over D, another finite collection of relations over E. If you prefer, think of E equals D and the phi as identity. Okay, which is fine. Here basically what, and then you have this thing, and now the question is this. So I give you some instance psi. So which is now n variables and some constraints which are basically either these Pi's or Qi's applied to this. So of CSP. So suppose I give you an instance psi of CSP thing. Question, yes instances. So question, the promise problem is the following. 1, is it satisfiable as an instance of CSP A? Or 2, it is not satisfiable. So the regular CSP problem would be, is it satisfiable or not? But now it will not, in the no case, you should only, it's only a no instance if it's not satisfiable as an instance of CSP B. And how do you take a CSP A instance and make a CSP B instance? It's kind of obvious. You just take each Pi and replace it by Qi. Obtained by replacing each Pi by Q. So the case when all Pi's are equals to Qi's, A equals P, is just the regular CSP problem. But in general, this is the problem. And why is this? So this is the promise problem. So this is a promise problem. So where does the term promise come from? So first of all, note that this is a well-posed problem. You can't be satisfiable as an instance of A and not be satisfiable as an instance of B. Because if you have a satisfying assignment for CSP A, you just apply phi to the satisfying assignments. You must get a satisfying assignment to CSP B. So these two, so basically the world of instances, you have these yes instances, you have these no instances, and they don't intersect, so it's well defined. And there is something in between which might be not satisfiable as an instance of A, but satisfiable as an instance of B. For example, that could be a 7 colorable graph, or graph with chromatic number 7 in this case. If you give me something like that, I don't care. You can say whatever you want. But these two cases, you should get correctly. So this is the decision version. Okay, decision question. You can also talk about a search question, which is that I can give you an instance and I promised you it is satisfiable according to A. Find me a satisfying assignment according to B. So that's the way I phrased this question. Given a 3 colorable graph, can you 10 color it? Right. So the decision version here would be that either you're 3 colorable or you're not 10 colorable. And this is a search version. And one thing which is important to note, that unlike the exact case, we do not know a general reduction from search to decision here. So if we had an oracle to tell you if a graph is 3 colorable or not, nothing else, you can just repeatedly query it in some clever way, some self-reduction, to actually make it help you find a 3 coloring. But if I only had this approximate promise oracle, I give you a graph, it will correctly tell me if the graph is 3 colorable or not 10 colorable. In between, it can give whatever answer it wants. Nobody knows how to use that to 10 color the graph or 25 color the graph or anything else for that matter, I think. So I don't think we understand this very well. Okay, but we will mostly study the decision version. And the point is our hardness results will hold for the decision version. Our algorithms invariably will solve the search version also, so we'll get the best of the both worlds. But there is this important search decision ingredient is missing in this theory. Yeah. All right. So now, okay. So that's promised CSP. So let's give some more examples, and then we'll close out, and then we'll pretty much talk about promised CSPs next week, and then we will see what to do after that. Yeah. So, all right, so let's do some examples. So I already told coloring, that's the most canonical one, but there's another one which really we started studying, which really started, which is what led us to the more general theory, which I call T out of KSAT. So here, colloquially, what is this problem? I give you a KSAT instance, and I believe I talked about this here maybe 3 years back or something, 2 years back or something. I give you a KSAT problem, and I promise to you that there is an assignment which satisfies at least T of the K literals in every clause. So T equals 1 being the regular KSAT thing. But then I only ask you to satisfy a normal in a normal way. So how can you write it as this particular thing? So A will be two relations, neg and this P. And what is neg? So neg is just this relation, which I think I might have told you this trick to encode negations. So if I have a single relation which just captures negation between two variables, I can negate any variable I want by introducing auxiliary variables. We are not in fast exponential land here, so variables are cheap and free. So you just use extra things if you want. Okay. And what is P? So P is basically all those x, let's say A in 0, 1 to the K, so this is KSAT, such that the Hamming weight of A is at least T, or A has at least T once. Okay, so T is some, okay, and B is going to be Q, come on, neg, and Q is basically 0, 1 to the K minus, you just don't like the all 0 sign. So as long as Hamming weight is at least 1, you're happy. So clearly Q contains P, and this is a promised CSP. Both D and E are Boolean. Phi is the identity, and pretty much most of the examples I'll give you will be like that. Okay. And this is a promised CSP. And you might recall, so it turns out that if T is at least K over 2 implies this PCO, I should also say some notation. So this problem I will denote as PCSP of A, comma B. Let's say. Clear papers just calls this as gamma is A, comma B and does PCSP gamma, but maybe this is better. You see both of these together. So PCSP A, comma B is in P. So if my promise is strong enough that a majority of the literals in each class are satisfiable, then this is polynomial time. And if T is less than K over 2, then PCSP AB is actually NP complete. So we have a sort of a clear dichotomy in this case. So this is something we showed with Ostrin and Hostad 3 years back. And somehow that was the starting point of the journey into PCSPs, because then we said, this is for all T and K. I think of T and K as fixed. Yeah.
K.
Yeah.
This kind of thing works for it.
Yeah. For all T, comma K. So for example, the smallest case like T equals 2 and K equals 5 was not known to be NP hard prior to what we did, and it's known to be NP hard. Okay, this is something we can show. And again, I don't think today I will get a chance to talk about polymorphisms, how they connect, but I'll do that next time. So we're almost getting up to 1. So let me give maybe 1 or 2 more examples. Okay, so one more example I can give in this spirit is A is P sub I and no negation now. So I equals 1 to K. No, K minus 1. B is not equal. Not all equal. So NAE. So what do I mean by this? So Pi is now all those guys with Hamming weight exactly. So again, I'm fixing K to be my arity, and the Hamming weight is exactly I. And NAE is not all equal. So this is another Boolean PCSP. So again, repeat the domain is for D and E are both 0, 1. So I have K is the arity. All the relations have the same arity K, no negations here. And now I tell you, A basically allows me to stipulate there are exactly I ones in some clause. But I is not 0 or K. So in particular, not all zeros and all ones are never allowed. And basically B will just have all of them not equal. And this is also a valid PCSP, because if you are satisfiable according to A, you are definitely satisfiable according to B. There's a homomorphism is the identity. Each Pi is contained in not only. So it turns out this PCSP, so again theorem, so this actually turns out to be in P. And a special case of this is nice, which is that so you allow all of these things, but I should also say that because of this, you don't have to allow all the I's here. So one special case of this would be, I can take any subset of this and the same thing still holds as well. For example, I can take A, so for example 1 in 3 sat. So I could give you an instance which is satisfiable as 1 in 3 sat, and then I can ask you to satisfy it according to not all equal 3 sat. Turns out this is a special case of this. All right.